Welcome back, and off we go. We're going to be looking, oh, we already looked at that. We're going to look at, there we go, reactions of amines with nitrous acid. I hope this sounds familiar. Nitrous acid is the conjugate acid of nitrite ion. And when you want to do this reaction, you always start with nitrite ion. Nitrous acid is not a very stable acid. You cannot buy it and then use it. You must buy nitrite, which is relatively stable, and then use it. And to generate nitrous acid, HCl is used in excess. And the nitrite ion becomes nitrous acid. And then a dehydration reaction happens if you protonate the OH to make it a better leaving group. Then the oxygen lone pair can kick it off, generating a nitrosyl cation. Nitrosyl cations are strong aminophiles. Whoa, I was doing some stuff that I forgot about. Bear with me here. Aminophile. And they will react with a variety of amines. We will explore the reaction with 2 of them and the non-reaction with the third amine. Primary amines will react. Not a very useful reaction, but here it goes. The nitrogen gets attacked. That's how oxygen gets neutralized. Then we have a tautomerization mechanism. Yes, that's what this is. Have you been keeping score of how many tautomerizations you've seen in 2 courses? It's over 10 by now. An H will be removed from one position and show up in another. Here it ends up on the O. Pi will move from this position to this position, and that is the 2 criteria for tautomerization. Pi moves, H atom moves. And we generate this, and this also looks a lot like a tautomerization, but something's leaving. So we're not making an isomer, we're making a whole new molecule with a different formula. It's an elimination. Protonate the OH to make it a better leaving group, and then do dehydration. Dehydration in gray. And that's how you form a diazonium ion. You will be doing this mechanism on a test coming up very soon. That's not a maybe, you will be doing it. And alkyl diazonium ions, they're very reactive and they will do many things. They could react with the chloride in an SN2 reaction. They could react with the chloride in an SN1 if you rearrange a hydrogen atom from this position to this position. You would generate a cation here, and that's how the chlorine ended up here. Similarly, water, which is present more than anything, look, aqueous, water's everywhere. Water could do the SN2 reaction, generate an alcohol. Water could wait for the rearrangement to a secondary cation and attack the cation, make this alcohol. You get a big fat mess. I think we've called that a dog's breakfast in the past. Not a useful reaction with primary amines and the Nitroseal Cation, which we know how to make now. That does not mean we will not be using primary amines to react with the diazonium ion, not the diazonium ion, the Nitroseal Cation to generate a diazonium ion. In fact, I hope you've started thinking about studying, because this is something we just studied. In chapter 22, we generated a diazonium ion from a primary aryl amine, benzoff. Primary aryl amine. It's not an alkyl amine. It's got an aromatic group on it. And we learned that those are stable at less than 5 degrees Celsius. And we can generate them using sodium nitrite, HCl, and 0 degrees Celsius. That would be an ice water bath surrounding your reaction mixture, wouldn't it? Generated aryl diazonium ion, which can do 7 useful things. React with the water present here to generate a phenol at room temperature, fluoroboric acid at room temperature to generate an aryl fluoride, copper 1 chloride and HCl at room temperature to generate an aryl chloride, copper plus 1 bromide, HCl room temperature to generate an aryl bromide, potassium cyanide, copper 1 cyanide room temperature, aryl cyanide, potassium iodide room temperature to generate an aryl iodide, and phosphorus acid, hypophosphorus acid, one less O than phosphorus acid, hypophosphorus acid, and it generates an unsubstituted aromatic. And we even saw when that was useful. So up here, not a great reaction with this primary amine, but if that was an aromatic ring, you're going to get a lot less problems that you have down here. Okay, now what happens with a secondary amine is a different result because you can't do this second step here. When the first H is gone, that's the only H here. And you would stop somewhere in a position near this. And here it is. The mechanism is pretty simple. Secondary attacks, just like the primary attacked. You generate this, but it can't, it won't undergo tautomerization. It'll just do an acid-base reaction. It will undergo tautomerization, but this is a more stable tautomer. It'll come back to this and eventually lose the hydrogen from here. And you get an N-nitrosamine. So think about this. If you're a smoker, one of the products of burning tobacco looks a lot like this secondary amine, and it generates a nitrosamine that looks a lot like this, and that is a known carcinogen. It generates cancer in your lungs. So that's one of the reasons smoking causes cancer. So nitrosyl compounds, they're, well, you know, they're dangerous. They're also useful for synthesis. I got through graduate school using a nitrosamine to do a reaction called a Diels-Alder reaction, and it served me well, but I had to be careful because the chemicals are dangerous. So do you see nitrogen gas being created here like we did here? The answer is no. Keep that in mind. Typically, these products are always yellow oils, and nitrosamines are almost always yellow oils, and they have a particular odor that's weird, but you don't need to know that. Tertiary amine, there's no H's on the nitrogen, so there's not going to be a reaction with the nitroseal cation. Instead, you get a reaction of the amine with HCl. I want to point out that this amine also reacts with HCl. It's equilibrium, and it goes back and forth with the HCl. It comes back here and does this eventually. Same for primary. Yes, it reacts with HCl, but it's in equilibrium with that, so it comes back to here and does this. This is never going to react with a nitroso. It's just going to do acid base. And typically, tertiary amines are not water soluble. They can't hydrogen, well, they can hydrogen bond with the water, but it's only as an acceptor. They don't have a hydrogen bond to donate to water. So they're not usually water soluble. But ammonium ions are very often water soluble because they're ions, and that enhances their water solubility. And that is a result you would observe here. You would take something where your amine was sitting on top of the water, not dissolving, looking a little like a little oil spill. And then all of a sudden you see it dissolve, and you've got this diagnostic use of the nitrosyl cation. If you had a primary amine, either here or down here, you'd see bubbles because the byproduct is always N2 leaving. If you had a secondary amine, you'd see a yellow oil due to a nitrosamine. And if you have a tertiary amine, you'd see the amine that wasn't dissolving in water before all of a sudden dissolves. There'd be no yellow oil, there'd be no bubbles. So what would your conclusion be if you saw something that wasn't dissolved suddenly dissolve? You'd say, oh, I must have had a tertiary amine. If you saw yellow oil, you'd say, ah, I must have had a secondary amine. If you see bubbles, you'd say I had a primary amine. And that's nitrosyl ion with alkylamines, usually a diagnostic test, not useful for synthesis. Aryl primary amines, very useful for synthesis, as we learned. And let's look at something else we can do with diazonium ions that relates to what we just saw. We made this molecule previously, and as promised, I said, I'll show you what we can do with it. If we can generate a beta-hydroxy primary amine, which we did using our nitroaldol just recently, nitroaldol product, or if you make a cyanohydrin, that's back in our past as well, and then reduce that, that's a beta-hydroxyamine. Both of these are beta-hydroxy primary amines. And you know what you can do with primary amines. Let me remind you. A primary amine under these conditions will generate, well, what are the conditions? HCl, excess AQ, and nitrite ion. They will first react to form Nitroseal Cation, which will then react with a primary amine to generate a diazonium ion, which will react some way. And this one makes a mess. This one makes useful stuff. But if it's beta to an alcohol, something else happens. And this is the only time I'm going to say this. It's a name reaction that I like the name. How can that be? I've always been harping on people, usually men, putting their names on reactions to boost their egos and stuff like that. I got to confess, I'm an oral learner. I use my ears and sounds help me remember things. And I just love the sound of this name, Tiffeneau-Demjanov. It's like poetry to my ears. So it's not that I like the two gentlemen. I like the way their names sound together. And if you react this primary amine under the conditions that'll make a diazonium ion, which are these, you will make this ring expanded ketone. Went from ring size 6 to 7, ring size 5 to 6. Wow, that's interesting. It's one of my favorite mechanisms too. Let's look at it. So as promised, you'll be generating a nitrosyl cation on your test, maybe twice now. It'll react with an amine. Here it's a beta-hydroxyamine, so you better be in tune for a Tiffeneau-Demjanov in your future. And what's going on here is tautomerization, followed by dehydration. And then the rearrangement happens. And look what happens. The carbon-carbon bond breaks from the alcohol carbon position. So this carbon here is going to end up attached here. Yep. And next door, there's going to be a cation because this carbon's losing a bond and not getting a bond back. There's the cation. Ring size is now 6. Let's count. 1, 2, 3, 4, and 5's no longer bonded here, but 5's bonded to this, which becomes 6. And there's 6. And this is one fast step away from becoming a ketone. I have a resonating O with a cation. That's why these cations are so stable. And it's easily eliminated here to make a ketone. So let's finish this segment by doing the whole mechanism from the very beginning. So we got to start with this part. And how does it go? We take our lone pair on our nitrite ion and protonate it. And blue second, because I think I can combine things here. Maybe even a green third. So what's going on? We've done the first part, protonation. So we would be here. What's next? The black is next. Oh, is this one time where I forgot to say black first, Grace? Oh, it should be written right down here. Black first, great. That's a typo in the book. You do that on a test, you lose a point. I should be punished equally. I don't know. Can I get a gray going on here? I hope it shows up. Could be invisible. It's almost invisible. Okay. So in this case, we're going to combine this, this, and this. So first was the black. We've got that in red. We better do this black in blue. It's second. And what is that black? You're going to protonate the same O. It's going to look it's going to look painful to your eyes. And it's going to go to HCl number 2. Yep. How can you do that? Well, isn't there a large excess of HCl? Isn't that given right in the question? Yes. This reaction requires a lot of HCl. And then the third step, lone pair on the O. Lone pair on the O resonates in and eliminates water. Lone pair on the O resonates in and water leaves. Water got an H from the red arrows. It got an H from the blue arrows. And if you don't like that, which I know, to me, that doesn't look nice. So maybe you just want to do this and then this. It's sometimes saving time is more confusing than helpful. So you have generated this species here. And for the purpose of brevity, we're not going to be changing this till near the end. We're generating R. And what's that going to do? And we also made, oh, wow, didn't even draw what I made. Better do that. N triple bond O plus. What's that called? What is that called? It's not on this page. It was called the Nitroseal Cation on the previous page. There it is right there. Nitroseal Cation. Let me remind you. And it gets attacked by the amine that's attached to R. I'm going to have a Cl minus lurking here. And what's going on? First step, attack the Nitroseal Cation. Pi breaks, becomes lone pair. And then you generate an ammonium. What happens to the ammonium? Yeah, I don't know. I don't know. I think I'm just going to keep it lurking there. Oh, yep, it's going to have a plus charge here. And N double O. And my Cl minus that was lurking takes an H. Maybe take the other H. Doesn't matter. Don't have to cross over a bond if I go this way. And what happens after you resonate in to make that pi bond? Resonate in to make the pi, protonate with HCl. It is a tautomerization. Oh, I don't need the lone pair, do I? And where are we? We're going to be here. Rn with an H. It still has a plus. Why does it have a plus? It has 4 bonds. 4 bonds. Oh, sorry, things got very green. So if I'm going to lose that O, I better protonate it. What am I going to protonate it with? HCl. We're doing this, right? Protonate the O with HCl to make it a better leaving group. What happens after that in baby blue? And up here was in gray. Cl grabs H, pi, leaving group leaves. Cl, which you did make another one of here, grabs H, sigma becomes pi, leaving group leaves. Oh, I can't use red arrows. They're not all the same step. Protonate first. Show me you know that. Now I get a diazonium ion that I need to draw out not just once, but twice. Let's draw out what I see over on the very left of the page. We see a square. We see a square attached to an OH. I'm going to show the sigma between the O and the H because it's going to break. We have a methyl here. We have a C with an N. Don't draw H2 because that's gone. What do we have? N triple N. Diazonium ion. And that is equivalent to same as verify to yourself these are the same. I'm going to rotate the sigma bond here. You don't have to. You can do this mechanism without doing that. In this one, I'm going to do the, I don't know if I had to do that at all. I'm going to do this rearrangement here. And this one, I'm going to do this rearrangement here. This bond can break or this bond. Look, take a look at my rearrangement. Where was it? Rearrangement happened right here. See? I could have broken this one or this one. Now, in this example, it didn't matter because it's all symmetrical in here. But here, my two carbons are not equivalent that are one away from the alcohol. So breaking this one here is the same as breaking this one. In this case, breaking this one is different than breaking this one. And let's try to see if we can combine some stuff. We're doing the rearrangement here and then the elimination here. I can do both those at once. This one first, though, you got to rearrange first, and I'll do exactly what I said earlier. I'm going to rearrange this one here. And I'm going to rearrange this one here. I know you don't like that. Well, I know I don't like that. Crossed over a bond there. But it's not the end of the world. And then this leaps. So that's the rearrangement step. This one right here. Those are different rearrangements, aren't they? And what's after that? Grab the H with chloride, make a pi between O and C. Why don't we do that right now? In a different color. Cl minus needs to be near the H. In baby blue, grab the H. Oh, now you're going to be really unhappy. I should have rotated the hydroxyl, not the sigma, off the ring. And same story here. There's nothing wrong with things overlapping, especially if you're using colors. Colors make it very clear. Grab H, sigma becomes pi. Make sure it ends between the two atoms. And which rearrangement gives which product? Which rearrangement is going to have the carbonyl between the two groups? That's this one. Well, here the carbonyl will be on one atom. And the next bond is going to be, this bond here doesn't break, right? So you'll have a carbonyl here. Next atom over is isopropyl. And next atom over will be this bond here, the methyl. That's this one over here. Want me to do some numbering to make it clear? Why not? We got to get to 5. Well, in both of them, we'll put a 1 on the carbon with the oxygen. And we'll just count around. So 4 has the methyl. And 4 ends up bonded to 5 with the rearrangement. And in this one, we'll do the same numbering. One was already bonded to 5, which has an isopropyl. 5 ends up with a new bond to 2. 5 ends up with a new bond to 2. 2 was always bonded to 3, which was always bonded to 4. And I hope you found that useful. It is a very cool reaction. And we're going to continue with further chapter 23 stuff after our break. And we'll see you then.